Hello everyone, my name is Shujo. Welcome to my ICML 2024 presentation on fair data representation at the Pareto frontier. This is a joint work with my advisor, Thomas Strummer. Today, I'll cover the motivation behind our work and then three theoretical results, which lead to our algorithm design and finally the numerical experiments. Uh, Fairness is now an urgent issue to address due to the increasing popularity of machine learning and AI in information sharing and decision making, especially considering the unbiased algorithms can inherit the bias in the data. Therefore, our goal here is to develop a method that can remove the biases directly from data. There are two fairness perspectives. One is group fairness, one is individual fairness. In this work, we focus on an important group fairness definition called statistical parity, which requires the learning outcome denoted by y hat to be statistically independent of the information or sensitive information z. The problem is non-trivial due to at least the following two reasons. One is that the sensitive information z can be highly correlated or dependent on other feature variables in the data. And another is the utility cost. So we don't really know how much utility cost is due to the additional statistical parity constraint on the learning outcome. Before our work, there are two remarkable papers that simultaneously proved the optimal fair regression can be characterized using Wasserstein-2 barycenter. I'll cover more details later. But a paper focused on one-dimensional regression. Also, the theoretical results does not generalize to a optimal trade-off between utility loss and statistical disparity. More importantly, such a theoretical result has a post-processing nature. Therefore, it cannot be used to develop pre-processing or fair synthetic data. And before our work, there is still a lacking of theoretical foundation or theoretical guarantee for how to design a fair data representation or fair synthetic data. Therefore, in this work, we aim to solve the two problems. One is a theoretically provable Pareto frontier, and another is a theoretical guarantee or theoretical foundation for how to design optimal fair data representation or optimal fair synthetic data. We also hope that to develop a method with explainability and practicality. Okay. To start, we first generalize the optimal regression, fair regression results from one-dimensional to arbitrary finite dimensionality. Here, x, y, z are independent variable, dependent variable, and sensitive variable. So the objective here is to minimize the distance between our y and the prediction, which is denoted by fxz. And for statistical parity, we require the prediction fxz to be independent of z. Our first result shows that there exists a unique solution to problem one, and it can be constructed as the following. So first, one finds the conditional expectation of y given xz, which is the optimal prediction in the L2 sense. Okay. After that, we find the sensitive group of the conditional expectation, which is denoted by conditional expectation sub z. Okay. After finding those prediction sensitive groups, we find the Wasserstein barycenter, which is the closest point on the Wasserstein space to those sensitive groups. Here, Wasserstein space is a metric space, consists of probability or data distributions. Okay, and after finding the barycenter, we construct those optimal transport maps T, now parameterized by the sensitive label Z, which maps those sensitive groups to the barycenter. And so that we can construct the unique solution to problem one, which is denoted by the conditional expectation bar here. And furthermore, we show that this infimum or lower bound, now we call the minimum loss for statistical parity, denoted by V squared, can be nicely decomposed into the following two parts. One is the L2 orthogonal projection loss. Another is the Waza-Stanton independence projection loss. Okay. To provide an intuition of this barycenter characterization, we perform k-means on the barycenter. So on the upper left, we have three sensitive groups, minus, plus, and cross. And on the upper right, we have the barycenter. On the lower left, we perform 5-mean clustering on the barycenter. And on the lower right, we look at the barycenter labeling on the original data. So we see that data points that share relatively similar location in their own sensitive group are actually sharing the same barycenter k-mean label, which means there is a multi-marginal matching effect on the barycenter. The barycenter is grouping data points that share relatively similar locations in their own sensitive group. In fact, how the barycenter is constructed is first find data points who share relatively similar location in the sensitive group, and then to form a match, and then represent the matched points by their Euclidean average. Okay, next, we move on to the Pareto frontier. To start, we need to relax the strict statistical parity constraint in problem one. To do so, we introduce the following statistical disparity quantification called Waza-Stanton disparity. It is denoted by d y hat z. It's defined as the average pairwise distance, Waza-Stanton distance between the sensitive groups. Okay, we adopt this quantification due to the following two desirable properties. One is that this d is a non-negative quantity, and it is equal to 0 if and only if the statistical parity is satisfied. So it characterizes the statistical parity constraint. Two, it has a very intuitive physics interpretation due to its definition in terms of Waza-Stanton space distance. It can be understood as the expected minimum amount of work required to move from one sensitive group to another. So after adopting this quantification, we obtain the following optimization problem. So for each of the D, what we call the disparity tolerance level, we now replace the strict statistical parity constraint by this relaxation constraint. So we bound this Waza-Stanton disparity by the tolerance level. And this is a natural relaxation to problem one. To see this, if we set tolerance level D equal to 0, then this problem reduces to problem one. Okay, so now this problem also characterizes the Pareto frontier. To see this, now for each of the D, we define the infimum as the minimum loss at the disparity tolerance level D, denoted by VD. So if one wants a lower utility loss than VD, then it is necessary to increase the disparity tolerance level than D due to its infimum definition. On the other hand, if we want to lower the tolerance level D, then it is necessary to cost more than the minimum utility loss, VD. So that's exactly the definition of a Pareto frontier. Our second main result shows that there is a very nice closed form solution to problem two, simply by replacing the optimal transport map in the solution to problem one by the Mackay interpolation. So here we replace the optimal transport map when we for the solution of problem one by the linear interpolation between the identity map and the optimal transport map. Here, T is the time parameterization. Therefore, for each tolerance level D, if we replace the original optimal transport map by the Mackay interpolation and set the time t to be equal to 1 minus d divided by square root v, where v is the minimum amount of work required for statistical parity. It's the infimum in problem 1. Then we obtain the optimal solution to problem 2 at the specific tolerance level d. And it is true for any d from 0 to square root v. And if d is more than square root v, then there's no trade-off because the tolerance level is so high that the conditional expectation automatically satisfies the constraint. Okay, instead of going through the technical details, I will talk about an Euclidean analogy to the trade-off. Okay, here on the Euclidean space, we have 3 data points, and we quantify the disparity by the dotted lines, which is the pairwise distance among them. And then we quantify the utility loss by the distance of between the current location and their original location. So how much they traveled is the utility loss. One can prove that the utility loss, which is the average length of the solid line, plus a scaled version of the disparity, which is a dotted line, is lower bounded by the standard deviation of the 3 points. Actually, it's true for arbitrary endpoints. And we showed in the paper, we proved that the same is happening on the Wasserstein space. So now each of the dots is a data distribution. And then if we replace the represent the dotted line by the Wasserstein disparity and the solid line by the L2 loss, and one can show that the L2 loss plus a scaled version of the Wasserstein disparity is lower bounded by this minimum, lower bounded by V, this minimum amount of work required to achieve this parity. And the equality is achieved if and only if those distributions are traveling along the Mackay interpolation. So when this lower bound is achieved, there is a clear linear trade-off between the utility loss and disparity, because when the equality is achieved, if one wants to further lower the utility loss, then disparity needs to go high. If one wants to further lower the disparity, the utility loss needs to go high. Next, we move on to the fair data representation. So although the above 2 theoretical results are nice, they assume the knowledge of the perfect prediction, which is the conditional expectation. So in practice, one needs to apply a machine learning model to estimate that conditional expectation first. That is what we call a post-processing nature of those 2 results. But such a post-processing nature has a lot of disadvantages when comparing to a pre-processing or fair data representation approach. We refer to our paper for more details on the disadvantages. Therefore, we want to design a fair data representation with the following thinking on objective and constraint. Okay, for the objective, so if we designed a fair data representation denoted by x tilde and y tilde, then a model trained on x tilde and y tilde is denoted by, let's denote it by f x tilde sub x tilde y tilde. Then the total utility loss is the distance between the true dependent variable and this trained model via our fair data representation. And this total utility loss is upper bounded by the distance between y and the perfect prediction using x tilde y tilde, plus the distance between the perfect prediction and the trained model. But notice that the second term is actually a training loss. So practitioners would aim to minimize this training loss. And therefore, our goal in designing x tilde y tilde is to minimize the first term so that combine the effort of two, one can achieve a low total utility loss. Okay. And for the constraint, we require the x tilde to be independent of z so that any measurable function taking only y tilde would be guaranteed to be independent of z. Also, one might also use both x tilde and z to generate predictor for y. Therefore, we also require the perfect prediction of y given x tilde and z to be independent of z under the following thinking. So if a model using x tilde and z is closer to the perfect prediction, then the more independent it should be with respect to the scientific information, because we require the perfect prediction to be independent of z. Okay, so now putting everything together, we have this optimal fair data representation optimization problem. And this admissible set essentially requires the x tilde y tilde to be measurable with respect to the original data. So it has the roots from the original data. Okay, so our third main result provides a characterization to the optimal solution of problem 3. So essentially, it tells us for the optimal choice of x tilde, we can just choose y bar, which is the Wasserstein barycenter of the sensitive groups on the independent variable x. Okay, so this sigma just means how much information contained by this random variable. And however, the difficulty comes from this equation. It's not clear in general that how can we construct a y tilde satisfy this equation. But the key observation here is that if the optimal transport map that transport the sensitive groups for the conditional expectation of y given x bar z to their barycenter are affine, then we can leverage the linearity of the conditional expectation operator in terms of y to directly apply those affine maps on y to deform and generate our optimal choice y tilde. Therefore, in our algorithm design, we adopted the affine transport maps to generate an affine estimation of the solution to problem 3, which is now denoted by xDAG and yDAG. Okay. Finally, we combine the Mackay interpolation, which is the solution to problem 2, and xDAG and yDAG, which is the affine estimation to the solution of problem 3. Putting those two together, we generate the fair data representation at the Pareto frontier, which is denoted by xDAG t parameterized by t and yDAG t. So xDAG t is the output of our algorithm 1, and yDAG t is the output of our algorithm 2. We test our method on several real data sets, and we test using logistic regression and random forest on classification and compare the result with the state-of-art learning representation methods. So here on the vertical axis, it's the area on the curve, so higher the better. On the horizontal axis, it's the quantification of discrimination using this definition. And for each of the cross on the plot, the center is the average for cross-validation, and the horizontal and vertical stick out are the standard deviation. So our method is in dark blue here, and the line is the Pareto frontier generated by our method. It is clear that our method outperformed the state-of-arts by achieving a higher area on the curve with the same discrimination. Also, our method since it generates the entire Pareto frontier, the practitioners can choose the desirable discrimination level and at the lowest utility loss. Okay. We also tested our method on one-dimensional regression and compared it with the true Bayes-Zenner method, which uses the matching of CDFs to find the true Bayes-Zenner. Okay, and here the vertical axis is the L2 loss or mean square loss. The horizontal axis is the Wasserstein-2 disparity. So our method is also in dark blue. You can see that from the plot, we achieved very similar results via linear regression and artificial neural networks when comparing to the true Bayes-Zenner method. But our method has several advantages when comparing to the true method. First, it generates the entire Pareto frontier so that practitioners can choose the optimal trade-off. Second, our method, since it uses affine maps, it's very efficient. To show that, I plot the timetable. For example, our method using linear regression only takes 1 second, when in comparison, the CDF matching method takes much longer. And also our method, since it only uses the first 2 moments, the average and covariance matrix, so it can be applied to arbitrary high-dimensional tabular data. So we also plot the Pareto frontier for high-dimensional tabular data. However, when deal with data with fluids, high-dimensional structures such as the image data, affine estimation doesn't work. So in order to bring out the true power of our theoretical results, we are now working on using neural network structure such as GAN or transformer to estimate the true optimal transform maps and the true Bayes-Zenner. This is an ongoing work to show a preliminary result. We are trying to unlearn this gender variable in the SLAP A dataset. So the first row is the true face image from the female group in SLAP A. And then we train an optimal transform map using gain structure neural networks to map those female to the male group. So the third row is actually the push for images, which are synthetic image. And the middle row is the Makai interpolation when t equal to 0.5. So it's the Bayes-Zenner. Okay, so visually we can see that it becomes very difficult to determine whether or not this middle row belongs to a male or female group. So I think that's a visualization of the satisfaction of the statistical parity constraint. But this is still an ongoing work, and we hope to develop some practical methods on more than tabular data, such as image and language data. Okay, so to summarize, in this work, we provided a concrete characterization for the optimal trade-off between utility loss and disparity. And also, we proposed a theoretically provable way to design fair data representation and combine the two results to develop fair data representation at the Pareto frontier. Thank you.